How's everyone doing today? So today we're going to talk about Bayes' theorem. Bayes' theorem is related to conditional probability. However, Bayes' theorem extends it to a variety of possibilities for that first event. So let's talk about probability for a second and review. If I have cup A and cup B, and they were exactly the same, and I didn't tell you which one you were picking out of, what's the probability that you're going to pick out of cup A? Well, there's two cups. There's one cup A, so you would say 1 out of 2. All right? So that should be review. Now we're going to think about our sample space as a rectangle. So for example, with cup A and cup B, we have two pieces to our rectangle. One is cup A, one is cup B. The probability of picking one, again, is 1 out of 2. If we wanted to take that rectangle and talk about the probability of tossing a coin twice, right? Probability, all right? So the outcomes would be, again, in our rectangle, all equal, right? Would be tail, tail, head, tail, tail, head, and head, head. So we can use this shape to really get a pictorial representation of probability. So let's go back to our cups, all right? Take this away. Let's go back to our cup A and cup B. And I'm going to add some information. In cup A, we have 20 red gumballs. And in cup B, I have 10 red and 10 white gumballs. And I'm going to alter the question a little bit. All right. You reach in to a cup, you don't know which cup, and you take out a red gumball. The question is, which cup did you draw from? All right, so we reach in and we take out a red gumball. The question is, which cup did you draw from? Well, we can create a picture by saying, here is cup A, and I've got 20 red. They're all red, right? Actually, you know what? I'm going to do it this way. I'm going to say we got 10 red over here and 10 red over here. And here is cup B. And we can put that into two parts because I have 10 reds and 10 whites. All right. Since we know that we've already chosen a red ball, right? We have two chances that we got into cup A out of 3 total pieces with red in it. So my probability that I chose from cup A is 2 out of a possible 3 where we could have gotten red gumballs. If I wanted the probability that I chose out of cup B, well, then I have 1 area with red out of a possible 3 areas with red. So it is indeed 1/3. So with this added piece of information, it takes our probability from just cup A and cup B of 1/2 to 2/3 and 1/3. If you understand this fairly straightforward problem, you have an idea about Bayes' theorem. All right. So let's take it out of the pictorial and bring it into the numeric. So with Bayes' theorem, we're deciding, let's say we wanted, given that we've chosen a red, what is the probability that we chose from cup B? All right, so here's the formula we're using. We're saying we want to know the probability that we chose out of cup B, given that we've already chosen a red ball. And that equals the probability of choosing cup B times the probability of choosing a red given it is in, not D, cup B, over the probability of a red ball. All right, so the probability of choosing cup B, right, since there's two cups, we want to know the probability of choosing cup B without any information, and that is 1/2. And then we want to know the probability of choosing a red given that we've picked B. So let's go back to our picture real quick. Here is cup B. So once I know I'm sticking my hand into cup B, I've got an equal amount of reds and whites, which means the probability of choosing a red would again be 1/2. So let's go back up. Let's label this 1/2. All right, and now we need the probability that we're choosing a red for our denominator. Let's go back to our picture and take a quick look. So how many red balls do we have? We have 30. How many total balls do we have? That is 40. And if we simplify this, it equals 3/4. So probability of just choosing a red would be 3/4. So let's scroll down. Let's put in the 3/4. And I like doing it this way. I like being able to say what each individual probability is before putting it into the formula, because very often you get caught up in what things mean. So listing it this way is really helpful. So let's put it into the formula. So I got 1/2 times 1/2, and my denominator is 3/4. All right, so why don't you pause the video, do the multiplication, and I'll see you on the back end. Okay, hopefully when you did the multiplication, I got 1/4, and I'm dividing by 3/4, which means I'm multiplying times 4/3. And I can cancel, and I wind up with 1/3, which if we scroll up, was what we got when we used our picture to get our probability. So that is another way to do it. All right, so here is a fairly classic problem. I think it's fairly timely based on the situation we're in. A certain disease occurs in 7/10 of our population. If a test for the disease results in a false negative rate of 1%, and a false positive rate of 5%. Calculate the probability that a person who tests positive will actually have the disease. Why don't you guys pause the video, take a minute to think about it, pull some information out of the problem. All right, so let's start with a general formula for Bayes' rule, and then we will start relating it to the information in the problem. So if I have the probability of event A given that B's already occurred, it equals the probability of A times the probability of B given A over probability of A times the probability of B given A plus probability of A complement, which means not A, times the probability of B given that not A has occurred. Now, very often these formulas are really confusing when you're just talking about A's and B's. But we have two things occurring in this particular problem. We have a disease, we have getting a disease, and we have testing positive. So let's relate event A as getting diseased, getting the disease. And let's do event B as testing positive. Why don't you guys take 30 seconds and let's redo the formula, but start putting in, instead of event A, put in probability of getting disease. Instead of B, put in testing positive. And let's see where we stand. So pause the video. Let's redo the formula. And we'll see where we're at. All right, so the first thing I would do in redoing this formula is reread that last sentence. It says, calculate the probability that a person who tests positive actually has the disease. So if that's the case, I want to do the probability that someone has the disease given that they have tested positive already. All right, so A disease, B positive. There we go. Looks good. So again, we're going to change all our A's to disease and B's to positives. So we need the probability of disease times the probability of testing positive, given that we have the disease, over probability of disease times the probability of testing positive given that they have the disease, plus probability of no disease times the probability of testing positive given that we have no disease. All right, so now I've taken the general formula. I've related A to having the disease, being sick, and B related to testing positive, and I've taken the formula out of the general form and made it very specific to this problem. I think this is really your first step. All right, this is very critical in the setup of the problem, but it makes everything a lot easier, because now we can start talking about the different components of the problem. So for example, the probability of being sick or having the disease, we said was 0.7%. Now we can't keep it as a percent, we have to put it into a decimal. So 0.007. Now we also need the probability of testing positive given that we're sick, right? That's the next piece that we need. That's this piece over here. So how are we going to do that? Well, we have a false negative rate of 1%. A false negative rate, negative means the test shows that you're not sick, but you really are, was 1%. So we need the true positive rate. So I would do, I would say you need 1 minus 0.01 to get the true positive rate. And that would be 0.99, which means that 99% of the people who have the disease will test positive. All right, now we also need our complements. So we need the probability of no disease, because that is part of our formula down here. And if 0.007 have the disease, we can do 1 minus 0.007 to get 0.993. And the last piece of information we need is the probability that you're going to test positive given that you are not sick or have no disease. And we can scroll up to our problem and say the false positive rate is 5%. So we can use that, because what false positive means is that you tested positive, but you're not sick. And that's what this probability tells us. So I'll say 0.05. All right, now that we have all of our components for our formula, why don't you guys pause the video, take a moment, and plug everything in, and then we'll see where we're at. All right, so hopefully by now you took a minute to plug everything in. So we have 0.007 times 0.99 divided by 0.007, 0.99 plus 0.993 times 0.05. All right, why don't you guys take a minute, plug it into the calculator, and then we will talk about the answer. All right, hopefully you plugged it into the calculator and you got 0.1225. If you did not, go back, double check your work. The calculator is a very big stickler for order of operations, so make sure your parentheses are all in the right place. If you have to, do it as multiple calculations, but try to avoid rounding until the very end. So what we should say at the end of this problem is that approximately 12.25 or 12.25% of the people who test positive for the disease actually have it. And there you go. There's Bayes' theorem. So why don't we try one more example. We have a shipment of 2 boxes, each containing 6 phones that's received by a store. Box 1 contains 1 defective phone. Box 2 contains 2 defective phones. After the boxes are unpacked, a phone is selected and found to be defective. Find the probability that it came from box 2. All right, so our 2 events are going to be, so A, we're going to talk about what box it came from. So probability of event A1 is going to be the probability that it came from box 1. Probability A2 is going to be probability it came from box 2. Our B event is going to be defective phone. All right, so we'll say that, right, a phone can either be defective or not defective based on the probability. So we need to know the probability that we came from box 2 given that our phone that we chose was defective. So utilizing our formula from the previous, we can start filling in some of these and say the probability we came from box 2 times the probability that we were defective given that we came from box 2 over the probability that we came from box 1 times the probability of being defective given that we've come from box 1 plus probability that we came from box 2 times the probability that we were defective given that we came from box 2. Now notice in the last problem I used the complement. However, here, the complement of being from box 1 would be being from box 2. So how the formula takes shape is up to you. You can use the complement if you'd like to, or you could say not box 1, or you could say if it's not box 1, it has to be box 2 because there's only 2 boxes. That is fine with me. All right, so looking back at the problem, we have 2 boxes, right? So the probability that we came from box 1 is going to be 1/2. The probability that we came from box 2 without any additional information is also going to be 1/2. All right, now if we're looking in box 1, right, given that we've chosen from box 1, the probability of being defective is 1 out of 6 because box 1 contains 1 defective phone, right? And each box has 6 phones. And the probability of being defective given that we came out of box 2, all right, so we had 1 defective phone in box 1, and box 2 in the problem says contains 2 defective phones. So you could write this as 2/6. You could write it as 1/3 if you wanted to. This is not your final answer, so it's up to you how you want to write it. But now let's get one more thing. We need the probability of not being defective given that we came from box 1. Well, if the probability of being defective coming from box 1 is 1/6, probability of not being defective in box 1 is 5/6. And we need the probability of not being defective given that we've reached into box 2, and that would be 4/6. All right. So at this point, why don't you pause the video and see if you can start filling in the formula. Okay, so at this point, let's say the probability of coming out of box 2, given that the phone we got was defective, well, the probability of coming out of box 2 is 1/2. Probability of defective coming out of box 2 is 2/6. Probability of coming out of box 1 is 1/2. Defective coming out of box 1 is 1/6. And we're going to add that to 1/2 times 2/6. All right, so 1/2 times 2/6, well, I can cancel, and I'm left with 1/6 on top. And then if I do 1/2 times 1/6, it's 1/12. And I do 1/2 times 2/6, it's 2/12. This is the reason why I didn't simplify those denominators, because I really wanted to not have to add them with unlike denominators. So I knew this would come out okay. So this is 1/6 divided by 3/12. Or I could say 1/6 times 12/3. And if I cancel, I wind up with 2/3. So the probability that my defective phone came out of box 2 is 2/3. When it comes to these word problems or application problems, I do like to see this final sentence. It tells me that you're able to take it just from a number. For example, we got the number 2/3, but it allows me to know that you understand what that 2/3 means in the context of the problem. So I definitely like to see it. Thank you for listening to my short chat on Bayes' theorem. At this point, it's a matter of going through the problem, picking out the relevant information, and then making sure that you're able to substitute it into the formula. So I'd love for you to practice a little bit more, and I will see you next time.